Here is the counterintuitive truth about programmable matter. The bottleneck is rarely the material. It is everything around it: power delivery, sensing, control, and proof. As of 2026, no general-purpose bulk programmable matter exists. What we really have is a family of specialized active materials. Each one works inside a narrow envelope. One or two actuation modes: limited force or limited speed, restricted environmental tolerance, and very real fatigue, drift, and hysteresis after repeated cycling. So when someone promises a wall becomes any object, translate that into something much less magical. Think a surface with a bounded set of verified states, known load limits, a defined energy budget, clear lockout conditions, and failure modes you can inspect and recover from. That framing matters because the most common commercial reality today is not reconfigurable bulk matter. It is programmable layers attached to conventional structures, tunable coatings, adaptive textiles, soft robotic elements, morphing components, responsive optics, replaceable modules that can be swapped when they age out. These are practical because they isolate risk. They also reduce how much power, wiring, and control complexity you have to distribute. The first high-impact finding is that reversibility is expensive, not just in energy, but in verification. To count as programmable, a system needs repeatable state changes, a defined program state, and a measurable end state. It also needs a reset path, a lockout, or a replacement plan. Without that, you do not have a deployable system. You have an impressive demo. Next, consider the material classes that show up again and again. Shape memory alloys and polymers can deliver strong shape change, but fatigue and thermal lag can dominate. Liquid crystal elastomers and responsive polymer networks can tune shape or stiffness, but durability and stability become the trade. Electroactive polymers can look like artificial muscle, yet voltage, encapsulation, and lifetime set the limits. Magnetoheological and electrorheological materials offer field-controlled stiffness and damping, but packaging and long-term stability are stubborn. Hydrogels and chemomechanical materials can swell under chemical or biological stimuli, but dehydration and slow response times are constant threats. Architected metamaterials can amplify local actuation into big property shifts, but tolerances and inspection drive the cost. Across all of these, the recurring bottleneck is routing energy or chemical potential to the active region. If you cannot deliver it without excess mass, heat, or wiring, your design collapses. And even if you can deliver it, you still have to verify that thousands or millions of tiny active regions reach the intended state. That leads to the second high-impact finding. Programmable matter is a measurement and quality assurance problem disguised as a materials problem. You do not get reliability by optimism. You get it by calibration, environmental testing, and state verification you can repeat. You also need data pipelines that can trace any claim back to the underlying measurements. A third finding is that the enabling breakthroughs are often software and workflow infrastructure, not a single miracle material. Simulation helps you avoid dead ends before you fabricate. Measurement software helps you quantify deformation and state consistently. The field compounds when simulation, optimization, fabrication, and measurement are linked into one loop. If you invest only in discovery, you accumulate prototypes. If you invest in the loop, you get systems. A fourth finding is that state control is inseparable from safety and governance. Active materials introduce variable properties into domains built around fixed properties. That creates certification gaps. For procurement, it is not enough to ask, does it work? You need a state verification protocol. You need acceptance thresholds, calibration procedures, inspection time, and duty cycle documentation. You need rollback behavior, including passive safe states, lockout conditions, and manual overrides. Without those elements, failure becomes subtle and dangerous. A material can get stuck in an intermediate state. It can partially actuate. It can hide fatigue until a mixed environmental load, heat plus humidity plus UV, pushes it over a cliff. In biohybrid pathways, the risk envelope expands further. Growth and metabolism are powerful, but they import biological uncertainty into a reliability regime that demands predictability. A fifth finding is the most strategic for capital allocation. The near-term win is not funding fantasies of universal reconfigurable matter. The near-term win is funding verification, qualification, and standards alongside materials development. If you do not, the field keeps generating demonstrations that cannot be certified, insured, or maintained. Looking out over the time horizons, the near window from 2026 to 2050 is dominated by bounded, narrow function layers and replaceable modules. From 2050 to 2100, larger area adaptive structures become plausible, but only where energy routing, embedded sensing, cycle life, and certification converge.